All right, so I welcome you to the second discussion and second video about difference equation. And this video is about solution of first order difference equations. So can I remind you what is a difference equation? So it is an equation where we have x of t, t is here time, it's some constant, let's call it instead of phi, we can also say a. It's x of t minus 1, and there is some also other constant term, let's call it b. Well, we want to find a solution. And what is a solution to a differential equation? It was a function. And the same is here. The solution to a difference equation will be a function x of t, something that is dependent on x of t. That explains how x of t is evolving, moving over time. It's a function. So the question is, how can we solve it? Well, there are different methods, and the first one I will discuss here with you is in the subsection 3.1. It's a so-called backward solution. And we differentiate, as you can imagine, between backward and forward solution. So let me first do a backward solution. Well, what is this about? In principle, let's call this my equation 1. We shift equation 1, one period into the past to t minus 1. That would imply, well, we have then on the left-hand side xt minus 1. Then we would have a, and the xt minus 1 into the past is then xt minus 2. Plus b. That gives you my equation 1. So we shift equation 1, that is the guy we want to solve, one period into the past, backwards. Therefore, it's called the backward solution because we shift it back. And now look, we have here a xt minus 1, and that is what we will substitute in now on the right-hand side. So that means substitute equation 2 in equation 1. So we have then x of t is my a. And now for xt minus 1, I use equation 2, that this is a, xt minus 2. That's wrong. All right. Xt minus 2 plus b. And then we have plus b as well here. Okay, well, this can be rewritten. This gives me an x squared term, xt minus 2. Then we would have here an ab term plus b if I multiply the a into the bracket. All right, so now look. Now you can imagine I can shift this equation 2 again one period into the past backward. Then I have here a t minus 2, and I can plug in this t minus 2, then gives me here then with a t minus 3 term and so on. So you can iterate this, step by step backwards. But what will you then obtain? Well, on the left-hand side, we will have this x of t. This is always going back one step more. But if it the 2 goes to 3, to 4, and let's say it goes to t, then we would have t minus t gives me an x0. But then what do we have here? The a would be, if the 2 is the t, would be then a to the power of t. So this converges, the first term converges at to the x0. And x0 is basically the starting point. When it starts. Starting point. In our case, as you remember, when we talk about the Solow Krauss theory, I always say there is an initial capital labor ratio. That's today's capital labor ratio, and that's what we know. We have a data point for x0, or for the initial capital labor ratio k0. That is this. And now look, what would we have here? These terms. Well, look, there is a b. We can factor out a b. So let me make an intermediate calculus. We can for sure factor out a b, and then we would have here this 1, this a, And actually, if we do this iteration more and more, we will see that it's a sum. So this is a sum, an infinite sum, yeah, because we have to do this iteration for infinite time periods. So that gives me an a to the, call it k, and the k starts at 0 to how many steps go we back? Well, we said we go back to t steps, then we have to do it for t minus 1, because look here, we did it for t1, and we have then these terms. So if we go to t minus 1, then we will get for period t here, yeah, we get this term, and that is then the terms we would obtain for the t minus 1 iterations. Okay, so this is what we would have from now. So my function, my solution function is a to the power of t. Look, my a is some term, yeah? And now let's say, let's assume, which is often the case, that a is also less than 1. The absolute value of a is less than 1. Yeah? Then we can simplify this condition further. Of course, this is a to the power of t. So with every time period, we just square. For the first, it's a. Then in the second, it's a squared, and so on. Yeah. So that gives me then, it can calculate then the value for the 10th time period. That would be a to the power of 10 times my initial value, plus b, which is a constant, no problem. But what is then this sum? Look, this is a finite sum. Yeah. So this is a finite sum. So let me write it here. Just a separate calculus. So write it here. T minus 1 a of k. And we know the formula for finite sum, right? It's 1 over a, 1 minus a to the t, because we discussed in the previous lecture that we did the finite sum up to t, and then it was t plus 1. And if we do then the sum to t minus 1, of course, then we have here a to the power of t. Okay, so that is what I can factor in. So it's a, 1 minus a to the power of t, 1 over a. And now you see this is the solution. This is really the solution we have obtained. It's a function. It's just dependent of a of t. All the other terms, this x0, this a, are numbers. So it's just dependent on time. Yeah. And when you want to know what is x at time t, time t10, you just plug in 10 here and 10 here, and you get a value, and you see the number. If you want to know for every, you can calculate for 0, what is the value of x at 0, at 1, and 2, and 3, and then you would see a function, how this function evolves over time. And that's a discrete function evolving over time. And that's my solution of a first order difference equation using the backward solution method. There's some interesting parts I want to briefly talk about this solution, because I can rewrite this solution I have got in the following form. So let me just write it again. So it's x of t, then we had a to the power of t x0 plus b, and it was this 1 minus a over t, 1 over 1 minus a. Well, look, I have an a of t here and an a of t here. So let me rewrite this a little bit and factor out then the at term. Then I have here an x0, and here the at term would give then an b over 1 minus a, and then I have also plus a b term 1 minus a. Now, so this is just another form to write it down, but in a moment you will see why this form is really a good form, and it has some advantage. In order to show this point, so I will study the solution of this difference equation similarly as we studied it for differential equation. What happens if the t goes to infinity with my solution function x of t? So what happens if t goes to infinity? Well, look, we know a is less than 1, and then we have 1 to the power of a large number. Well, that goes to 0. That means the first term will be 0, and this term will be 0. So what it is, it's just converging to b over 1 minus a, right? Because this will be 0. The a to the power of t is going to 0. 0 times something is 0. That term is 0, so we just have then the b, yeah, over 1 minus a. So this, and basically what this is, we know when the model is going up to infinity to a certain level, it's called the steady state level. That's the steady state. Yeah, it's our conversions level, the steady state level. And the steady state level, yeah, we can label it as x0 or as x steady state, right? That is what we know from our discussion also in differential equations. And now going back to this form, given that I know the steady state level, I can now rewrite the x, so this is the solution, so let me call it x solve, solve. I see now I can rewrite this solution as follows. This is a to the power of t, x0 is my starting point, minus, look what we have here inside the bracket is the steady state, so it's minus the steady state, and then plus what we have here, again, is also the steady state. So in principle, and now you see the advantage why I have rearranged it in that form, you can really, in a compact form, you can write the solution of this first order difference equation by x0, the starting point, minus the steady state point, times this at over time, plus steady state. Yeah? And so if you want now to iterate, if you say, okay, what is the function, I want to know what is x at 10 for t10, you just plug in here 10, and this term, x0 minus xx, this is a constant, right? Because xx is xs is a number, this is a number, so you just have here numbers and you just iterate, you multiply it with the respective a is also a number to the power of 10 for t here. Yeah? Okay, so this is a very influential method, this backward solution method, and it's natural for, in particular in physics, in science, because you just want to know where is my rocket, yeah, for each time step. Looking back, I know the rocket where it's today, and I want to know where was the rocket each time period before. The problem, however, is in economics, we often have not a backward problem, we have a forward, yeah? The so-called forward problem. And what is the forward problem? We say, okay, suppose my price today is dependent from the expected price, the expectations I built from today, over the price tomorrow. So I have the price of my car, of course, is dependent on whether I would buy it today. Well, what is the price tomorrow? Suppose the price tomorrow is lower, of course, then I will not buy it today, I will buy it tomorrow. So this is a forward problem because my price function is also dependent from my expectations on the price tomorrow. Yeah, that's a typical forward problem. And these problems are very common in economics, less common in science and physics. Again, that illustrates that economics is far more mathematically challenging than physics, biology, or some other natural sciences. Okay, so the final point when we talk about solution methods is how can we do it if we have, if we do it and apply it with the so-called forward methodology. So that's my third part, 2, which is the solution methods, but here the forward solution. And of course, you can imagine that this almost works in parallel to what we have discussed, just the other way round. So suppose we have again a function xt, and instead of a, let me call it now alpha, and not in order not to mix up it with the previous backward solution, x times x of t minus 1 plus a beta term. Okay, that's a problem. Now the forward solution means we shift, let's call this is my equation 1. So take equation 1 and shift it into the future, so t plus 1. Well, then we have, on the right-hand side, we would have then x, oh, sorry, here, of course, it's a forward problem. We have here t plus 1, yeah, of course, in the equation 1. So if we shift it now to the future, we would get here the xt plus 1 on the left-hand side, then we have the alpha, then we would have the xt plus 2, because we shifted one period into the future, and then we have here plus beta. Alpha and beta are numbers independent of time. Okay, this is my equation 2. Now substitute equation 2 in equation 1, yeah, because we have here equation 2 and we substitute it at that point here into equation 1. What do we obtain? We obtain then on the left hand side is my xt, and then we have alpha. Here we plug now for xt plus we plug in the equation 2, which is alpha xt plus 2 plus beta plus beta. Okay, then we multiply out the bracket. We have an alpha square xt plus 2 plus alpha beta plus beta. Okay, again, this can be iterated. Then we would have xt on the left-hand side. And now this is iterated, of course, also to the power of t. And when we iterate it here to the power of t, of course, we then have here a term which is xt to some, so it's not going backward, it's going forward, right? So we have plus, let's call it capital T. And this x capital T is a terminal condition, yeah, a terminal point, which is what is the level at the end, yeah, in future. So that is, of course, should be given. And then, of course, you see here that gives me again an infinite sum where I can factor out the beta term, and that is then from k0 alpha k to t minus 1. It's the same idea than we discussed in the backward solution. And of course, if I assume that here the absolute value of alpha is less than 1, then also this term here, beta, converges to this finite sum. We already know it is alpha, it's 1 minus alpha t over 1 minus alpha. So it should converge to this. And of course, that can also be rewritten with steady state points as we discussed a moment ago in the backward solution. So this is what we call the forward solution. You see it basically follows the same process. Again, we have here, that's a solution because it gives me my function, yeah, dependent on time. And it's just dependent here, you adjust alpha and beta, as you know, is a number, and you just have to put then for t the respective t you want to know, or if you want to plot the function, then you plot it for t1, t2, t3, t4, and so on, and you get then a discrete function for this approximation. Of course, there is a relationship between the alpha and the beta, between the a and the alpha and the beta. So the alpha, in this case of the forward solution, is the same as the 1 over a, is the same of 1 over a. So if you plug in the backward solution 1 over alpha in, you would get this solution. And for beta, you can show the beta is related, of course, to a term like minus b over a. So in other words, if I plug in here for alpha 1 over a, yeah, and for beta this guy, you can convert this function to the backward solution we obtained above. Or if you plug in the above for a and b, yeah, respective the terms here, yeah, the reverse terms, you can also convert it into the other direction. The important point I just want to emphasize at that point, that here we assume alpha is less than 1. In the backward solution, right, we assume that a is less than 1. But look, this is not the same, because if I say alpha is also 1 over a is less than 1, then you see immediately that this condition for the forward solution is not the same we have in the backward solution, because this condition would mean that a is greater than 1, yeah, in this forward solution. Yeah, that is what you have to take care of a little bit when you work in this with backward and forward solutions. Okay, so we have seen here in this short video that we can solve first order difference equations with the backward and the forward solution method. In the next video, I will discuss a generalization and I will do some explicit example. So see you soon in the next video. Have a good day. Bye bye.